Hi everyone. Today I'm going to introduce our paper called Denoising and Selecting Pseudo-Heatmaps for Semi-Supervised Human Pose Estimation. My name is Manchen Wang. My co-authors and I are from Amazon AWS AI Labs. 2D human pose estimation has been a fundamental yet challenging problem in computer vision. The goal is to localize human key points including elbow, wrists, etc. However, obtaining a fully labeled dataset at scale is extremely expensive in terms of both time and budget. To mitigate the annotation cost in this work, we aim at building high-performing human pose estimation model by training simultaneously on small labeled and large unlabeled datasets using semi-supervised learning. A key mechanism in recent SSL method is the use of so-called pseudo-labels. In the case of human pose estimation, it comes in the form of 2D heat maps, which we call pseudo-heatmaps. The main challenge comes from predicting pseudo-heatmaps that are reliable across all key points, especially on challenging torso joints such as wrist and ankle. To address this, we propose a novel training scheme which improves the quality of pseudo-heatmaps. In details, our approach employs a dual-student framework and enhances it through a denoising scheme and an uncertainty-guided pseudo-heatmap selection for cross-student training. To evaluate our design, we experiment using MS COCO dataset and achieve state-of-the-art performance. Before diving into the approach, we first revisit a recent work which introduces a dual-student framework for semi-supervised pose estimation, known as dual-pose. Dual-pose trains two student network, theta and COCO jointly, and employs the output from one network as a learning target to supervise the other. To derive the learning targets on unlabeled images, the heat map predicted on weakly augmented view are used as a pseudo-ground truth. While being simple, this framework can produce unreliable learning targets on unlabeled data. Its pseudo-heatmaps can be noisy as they are estimated from a single random weakly augmented view. As a consequence, the model may feed on this noise and exacerbate the training error propagation. To mitigate this problem, we propose two denoising solutions. First, we conduct multi-view augmentation by applying K additional strong affine transformation on the input image to produce more variants. Our key insight is that by adding richer stochastic perturbations in the input space, we can cancel out mistakes and noise in learning targets caused by the randomness in one single weakly augmented view. We further ensemble the set of candidate pseudo-heatmaps to derive more reliable learning targets by taking the maximum score per pixel over outputs of all augmented views. Second, we employ a threshold and refine scheme to further denoise the pseudo-heatmaps in cleaner responses. This scheme is similar to the confidence-based thresholding used in existing semi-supervised image classification methods such as fixed match, but we specially designed it for generating pseudo-heatmaps in human pose estimation by applying a 2D Gaussian centered as a location corresponding to the maximum response, if that response is above than a predefined threshold tau. In dual-student framework training, another issue we noticed is that the two student network theta and COCO can perform differently, even when predicting the same joint in the same image. Importantly, one student may output more reliable learning targets than the other, and we can exploit this information to further improve the final pseudo-heatmaps used for cross-training. For this, we propose to select the most accurate pseudo-heatmaps using an uncertainty-guided selection scheme that rejects a heatmap with higher uncertainty score. More in detail, we first compute the uncertainty as the pixel-wise standard deviation across a set of heatmaps predicted on multiple augmented view. Then, we select the more reliable outputs as pseudo-heatmaps. Specifically, we trust one student's own output over the other student when its uncertainty score are lower than a certain margin delta than those of the other student. We validate the performance of our method on COCO dataset under two evaluation protocols. COCO partial and COCO additional. COCO partial splits COCO train 2017 set ranging from 0.5,000 to 10,000 incremental labeled set and use the remaining images as unlabeled data. We compare our approach with other state-of-the-art semi-supervised post-estimation models and COCO validation 2017 datasets. In terms of AP, this table demonstrates the stronger performance of our model and its ability to leverage more reliable Pseudo-Heatmaps to achieve better generalization. Our model consistently outperformed the best competitor dual pose under all setups, including using different number of labeled images, backbone networks, and data augmentation strategies. In particular, we find it performs especially well in low data regime. For example, when using 0.5,000 or 1,000 labeled images, our improved margin over dual pose are significantly larger, up to 7.22. To study the effect of training on dataset of larger scale, COCO additional evaluation protocol uses COCO train 2017 as label set and COCO unlabeled 2017 as unlabeled set. To exploit unlabeled data in the wild, we also experiment by expanding the unlabeled set with AI Challenger. We experiment with different backbone networks and compare with state-of-the-art competitors. We find that training with unlabeled data from COCO Unlabeled 2017 and AI Challenger gives the best results for all backbones. For instance, when using ResNet 50 as backbone, our model achieves 73.3 AP, which is better than 72.3 by dual pose. We now ablate each component of our model, including denoising pseudo-heatmaps and uncertainty-guided selection. In left table, we analyze the effect of multi-view augmentations. As described earlier, we augment each image into K-strong and 1-weak views. Here, we evaluate this choice against different data augmentation and aggregation strategies. Results show that taking the maximum response is better than average. Furthermore, adding K additional augmentations, either weak or strong, always greatly improve the model performance. Lastly, we find that using K-strong views is more effective than using K-weak ones because it provides more diverse variations in input space. In middle table, we study the effect of the threshold and refine scheme. We change the threshold when applying thresholding on pseudo-heatmaps and compare results with and without refining pseudo-heatmaps with 2D Gaussian. It shows the benefit of applying both to remove the low responses, as well as producing cleaner responses in pseudo-heatmaps. In right figure, we ablate the effect of uncertainty-guided pseudo-heatmap selection by removing the uncertainty component from our model. We observe that using the uncertainty estimator to select the pseudo-heatmaps gives significantly better performance than not using it. Interestingly, no matter with or without uncertainty, model performance is improved as we increase the number of augmented views, validating the previous hypothesis that multiple views are important and showcasing the complementary of our multi-view and uncertainty contributions. That's all for my presentation. Thank you for watching. Here are some visual results.